Hey, guess what time it is, class? It's science time. Now take out your notes and let's get learning. Welcome back, class. So today we're going to be going over how to go about making dilutions and then also how to go about calculating the concentration of a diluted solution. So the first step has to do with the process of how do you go about making the dilution. So the first thing you do is you pour the correct amount of solution to be diluted into a volumetric flask. If you remember, that's the tall, skinny flask here where it has like a bulb at the bottom of it. It has a long neck with a mark part way up on this neck. And if you bring up to that mark, you have exactly that volume. Unfortunately, it's kind of hard for me to describe it when I don't have one here beside me to show it to you. So you bring it up to that volume. Then you pour in enough solvent, usually water, to almost fill the bulb of the flask. And the reason why you don't bring it up to the neck, the skinny part, is because you cannot stir it when it's up in that section there. Then when the bulb is only about halfway filled, you start swirling the flask to mix the solution. And once it's all carefully been mixed together here, you want to carefully add enough solvent to the correct volume. So in other words, at that point, you go ahead and bring the volume up to the top or to that mark along the neck of it. Now the way that you go about calculating the solution here, so the solution can be made less concentrated by diluting it with solvent. In other words, most often you can dilute it by adding more water to it. Now here's one of the key things though, is the number of moles of solute does not change when a solution is diluted. In other words, the total amount of substance that's been dissolved in there. When you add more water, you're not adding any more material, you're not taking away more material. You're adding more water, but the stuff that's been dissolved, you're not increasing or decreasing it. That remains the fixed amount. So the number of moles of solute before the dilution will equal the number of moles after the dilution. In other words, the moles before will equal the moles after. And this is something that's going to be kind of critical here in a little bit. So let's use this as an example here. We have these, let's pretend each one of these little dots here represents a mole. Okay? Or I'm sorry, each one of these little dots here represents a particle. So I have, in this case here, 1 mole, or it's kind of like saying I have 1 dozen of those particles within this. And this is a 1 liter container, so I have 1 mole and 1 liter, so I have a 1 molar solution. Then, if I were to increase the volume of that, if I were to double it, I still have the same number of particles. I still have a dozen, or in this case, I still have 1 mole, but now I went from 1 liter to 2 liters. So if you notice here, I still have 1 mole at the beginning, I had 1 mole at the end of it. So the moles before will equal the moles after. But I went from 1 liter to 2 liters. So by doubling the volume, my concentration has dropped. So initially I had 1 molar, and then over here I now have half the concentration. It's now a 0.5 molar. In other words, if I were to split this in half, okay, so now because this is a 2 liter container, I would have 1 liter over here, I have 1 liter over here, so I have a half a dozen over here, and I have half a dozen over here. Or basically, it's like me saying I have a half a mole for every 1 liter. So I have a half a mole in 1 liter, half a mole in 1 liter. So again, the moles before will equal the moles after the reaction, or after the dilution. So as the volume goes up, the concentration will always go down. So again, the moles will equal the moles. Now, if you remember, with the molarity, the formula for molarity, a molarity was equal to moles all over liters. So if you rearrange this and solve for moles, a mole is equal to the molarity times the volume, which is measured in liters. So in other words, if I take molarity times liters, or in other words, or molarity times volume, that would equal a mole. So if you remember, mole equals mole, or in this case here, moles before equals moles after. And since a mole is equal to molarity times liters, or the concentration times the volume, we end up with this equation here. You'll see C1V1 is equal to C2V2. Now, in some textbooks, you might see this as M1. I'll put down over here. Sometimes you'll see this as M1 times V1 is equal to M2 times V2. It's the same thing. So some textbooks will say C1V1 is equal to C2V2. Other textbooks will say M1V1 is equal to M2V2. So the concentration is measured in molarity. Volume is measured in units of liters. So basically the moles before the dilution will equal the moles after the dilution. So to give you an example here, let's pretend I have a half a liter container and I have a dozen particles. So in other words, we're going to say this is 1 mole. So technically this is a 2 molar concentration, guys. I have 1 mole in 0.5 liters. 1 divided by 0.5 is 2. So this is what's referred to as my stock solution or my reagent solution. This is the starting concentration. This is the stuff that has the highest concentration. It's kind of like in my chemical stock room. A lot of times when I get the solution, like for hydrochloric, that's most often a 12 molar hydrochloric acid solution. But what you work with in the lab is most often like 1, sometimes 0.5, sometimes it's 0.1 molar, depending upon the type of experiment which is being done. So what I have to do is I have to go from 12 molar to maybe like 0.5 molar. So I have to go through some dilutions in order to get to that point. So I'm always making it more diluted. So if you think about this, if I take this solution, which is right now is a 2 molar solution, let's say I pour it into another container. I know, amazing graphics here. And I pour some into the other container, or let's say I pour half of it into another container. Now, I originally had a dozen particles in each one, but now I have 6 over here and I have 6 over here. In other words, I have a half a dozen here and I poured half of it out. I initially had a 0.5 liters, but now I have 0.25. But if you notice this, 0.5 divided by 0.25 is still a 2 molar solution. Let me use this example here. If you're making some lemonade and you're using that instant mix lemonade, and you make a pitcher of it, and you put it into a pitcher here, stir it up, get everything dissolved, and if you ever taste it, it's going to have a certain amount of sweetness to it, or certain, a very distinctive taste to it. If you pour it into a cup, if you simply pour it into another cup and taste the lemonade directly from the cup, does it taste any different than if you were to taste it in the pitcher? So this is kind of like, this is the cup and this is the pitcher. When you pour it into the cup, the concentration of this is going to be exactly the same concentration as what it was inside the pitcher. So it has the same concentration. Now, let's say you taste this and all of a sudden you realize, ooh, that's kind of sweet. It's a little too sweet for my like. So what you end up doing here is, in order to make it more dilute, it's very difficult to actually take the stuff out. So what do most people do when something is too sweet? They're going to add some more water to it. So by bringing the volume up, so initially I had 0.25 liters, I still have the same number of particles, I still have 0.5 moles. But I now doubled the volume to 0.5 liters, and now I went from 2 molar to 1 molar. So again, if you notice here, 0.5 moles, 0.25 liters is a 2 molar solution. If I were to double the volume to 0.5 liters, the number of particles that's been dissolved remains the same. So this remains the same, but I doubled the volume. I now brought the concentration from 2 molar to 1 molar. So by increasing the volume, you will decrease the concentration. You'll decrease the molarity of it. So here's like a little example here. To prepare a 100 milliliters of a 0.4 molar magnesium sulfate from a stock solution of 2 molar magnesium sulfate. So one thing I would recommend doing is, whenever you're doing this, set this up as before and after the dilution. So you have your M1, your V1, your M2, your V2, or you might have C1, V1, C2, V2. It doesn't matter which one you pick here. So before you made any dilution, this was a 2 molar solution here. Whenever you see a stock solution, sometimes called stock, sometimes they refer to it as a reagent, that's your starting material. Okay, it's 2 molar. And But at the end, I want to have a 0.4 molar, and I want 100 milliliters. So when it's done, this is how concentrated I want, and this is the volume that I want. So the question is how much material do I have to take out of here to give me this concentration over here? And this is something that I have to do quite a bit whenever I'm preparing for a lab. And I know that you guys need to have a certain concentration. I need for all the classes, I need a certain volume of it. I have this much stock material. Is how much material do I have to take out of it in order to give me that solution here? So this is something that I have to do quite a bit in preparation for a lot of the labs. So the way that you go about doing this is, again, you set up the equation M1 V1 is equal to M2 V2, or C1 times V1 is equal to C2 times V2, and you just plug in the values. So initially the concentration is 2 molar. I don't know how much material is needed here, but in the end I want a 0.4 molar and I want 100 milliliters. But you have to convert 100 milliliters into liters, which is 0.1 liters. And you're just solving for V1. So in order to solve for V1, I have to divide out the 2 molar. So I end up with 0.4 times 0.1, which is what I have over here, and divide out the 2 molar. So this goes in the denominator. And when you do that, you end up with 0.02 liters. Now, most often in labs here, when you're measuring out volumes, most often it's not in the unit of liters, it's most often in milliliters. So 1,000 milliliters is equal to 1 liter. So a little conversion is 20 milliliters. So basically what this means here, the interpretation is I have to use 20 milliliters of a 2 molar magnesium sulfate and dilute with distilled water to 100 milliliters to make a 0.4 molar magnesium sulfate. So let me see if I can try to diagram this. All right, so I have initially, let's see if I can do this over here. I have a stock solution. Okay, and this is a 2 molar concentration. All right. Now, so what this means is I have to take out of here. I have to pour some into another container. Let's see, this is like a graduated cylinder. And I'm going to pour out of here 20 milliliters. This is not easy to do with the mouse here. Now when I pour this into the other container, this still has a concentration of 2 molar. Okay, but then in order to make this into 0.4 molar, and I need 100 milliliters, in other words, if I bring this volume up to 100 milliliters. Now, a common mistake that's often made here is that is the final volume. You don't add 100 milliliters on top of that, otherwise it'll be 120 milliliters. If this is a graduated cylinder, I'm bringing this first measure 20 milliliters, and I bring it up to 100 milliliters. In other words, I'm going to be adding another 80 milliliters on top of that. And when that happens, this is no longer going to be a 2 molar solution here. This is now going to be a 0. If you can see that or not, 0.4 molar concentration. So here's my stock. I first had to pour out 20 milliliters and then bring the volume up to 100 milliliters, and it will have gone from a concentration of 2 molar to 0.4 molar. So basically that's what that calculation will tell you here. So let's do some examples. I'm going to work these out, and then there will be a Moodle assignment that you're going to be doing with similar types of problems. So number 1, a solution is made by diluting 150 milliliters of a 0.12 molar ferric nitrate solution with water to a final volume of 0.5 liters. Calculate the molarity of ferric nitrate in the diluted solution. So before we get started with the first problem, let me do something a little bit more visual, and hopefully this will help strengthen your understanding of what's going on. All right, so let's start off with the equation. So the equation here is C1 V1 is equal to C2 V2. Okay, or sometimes in some textbooks you might even see is M1 V1 is equal to M2 V2. It's the same thing here. C stands for concentration, but a lot of times the concentration is in the unit of molarity. V stands for volume, and technically this is not correct because this is units and this is what you're solving for. In other words, you're solving for volume. But most often the concentration needs to be in the unit of molarity, and volume is going to be in the unit of liters. Now you can sometimes have other units as well, but for everything that you're going to be dealing with, just leave everything in the unit of molarity. So molarity liters and molarity and liters over here. Now we're trying to make it a little bit more visual what's going on. Let's say we have a container, and within this container we have each dot represent 1 mole. So a dot is equal to 1 mole. And let's say this is a 3-liter container. So therefore, if you look at the concentration of this, this will be, I would have a total of 12 moles in 3 liters. So the units for that, this reduces down to 4 moles per liter, or 4 molar. Okay. Now, sometimes this is what's referred to as the stock or the reagent solution. In other words, this is where all the solutions are coming out of this one container here. So it's kind of like a pitcher of lemonade. The pitcher is the stock. All the little cups are what the stock is being distributed to. So now, if I need to make a dilution, and I want to pour this into another container here. So let's say I'm going to pour this into a little bit larger container. But initially, I only pour out 1 liter of it. So this 1 liter right here is being poured into here. So in doing so, I would have 1 liter, and I would have 4 of those dots would go across. In other words, I would have 4 moles. So right now, I would have 4 moles in 1 liter, or also known as 4 molar. And I have 1 liter of it. So right now, this is my C1. My V1 is 1 liter. So the 1s are what you have before you do anything. The 2s are after the dilution. So sometimes you might say it's C sub I or V sub I stands for initial concentration, initial volume, or 1s and 2s, or A's and B's, or whatever here. But in this case, we're just using 1s. So I have 4 molar, I have 1 liter. So that's my C1 and my V1. So now I'm going to bring the volume of this up to, let's say, 4 liters. I'm going to add 4 more liters to this. So when I do so, and I don't have enough room here, but let's pretend that's 4 liters here. Okay. So therefore, the total number of particles I have dissolved within this is now going to be in here, okay, evenly distributed here. So now my V2 is now 4 liters. The question is, what is my C2? What is my new concentration? So this is where C1 V1 is equal to C2 V2. I don't know what is my new concentration. So since these two are being multiplied to each other, I need to divide out the V2. So therefore, I would end up with C2 is equal to C1 V1 all over V2. So my C1 was 4 molar. My V1 was 1 liter. My V2 is 4 liters. Now you really don't even need a calculator for this here, but 4 times 1 is 4, divided by 4 is 1. So this in unit liters will cancel out, so this will be a 1 molar solution. So this should be 1 molar. So if you think about this, if this is a 4 liter container, that means, here's 1 liter, there's another liter, there's another liter, there's another liter. For every 1 liter, so this will be 1 liter, another 1 liter, another 1 liter, and this will be the next 1 liter. For every 1 liter, I would have 1 mole of that solution in here. So this is technically 1 mole per liter. So we just found out that, initially we poured in here, we had a 4 molar solution. I only had 1 liter of it. This over here doesn't matter. So we're looking at before the dilution took place, what was the concentration and how much did you have? Then you brought the volume up to 4 liters, and you would now have the solution would have gone from 4 molar to 1 molar. And if you notice with the volume, it went from 1 liter to 4 liters. Now, one common mistake that's often done with this is that when you're adding the volume to this, it's always what is the starting volume, like in this case 1 liter, and what is the final volume, 4 liters. Even though you added 3 liters additional to it, it's not 3, it's 4. So you only are recording what did it actually go up to. And as you can see here, just from this diagram, it works out by what is the final volume, not how much additional volume is added to it. So hopefully that makes sense. So when you're dealing with the dilution, all that you're doing is just a proportionality. Basically, this right here is the vast majority of the work that you have to do here, is that you just have to rearrange this equation and solve for one of the unknown variables. Now we could include some of the work that you had done in the previous part, where if you have like so many grams, how many moles to liters, but then sometimes that's to prepare the solution. And then once you have this solution, and then when you're making a dilution, you're making it an even weaker solution. So let's go ahead and work out the first one. All right, so for the first one, one thing you're going to see is for dilutions, these are really easy to do. Once you've seen maybe a couple of these, basically they're all worked out the same way. Now, something that's going to be sometimes confusing is knowing, is this the initial, is this the final, which way you're going with that here. So sometimes you have to read the problem carefully and try to figure out exactly what's going on. So just like previously with the molarity, one thing I would recommend doing is writing down your givens. So we want to have your before the dilution has to equal the after the dilution. And before, we have the C1 and the V1. And the after, we have the C2 and the V2. So this is when you add the extra water to it and you bring the volume up. Now, one thing you will always see happening here is whenever dilutions take place, the concentration should always get less. At the same time, the volume should always get larger. So think about it, is if you have a pitcher of lemonade and you want to make it's too sweet, you need to dilute it down. You have to increase the volume to decrease the concentration. You cannot increase the concentration. The only way you can do that is through evaporation. We're not going to get into evaporating or distilling the stuff here, where, yes, technically you could make it more concentrated, but in order to do so, you have to reduce the volume. But for dilution, you're always adding additional solvent to lower the concentration. So this should be large, the concentration should be large, and this concentration should always be lower. This volume should always be smaller, and this volume should always be larger. All right, so when you look at the first problem, just write down the information that you have. So you have a 0.12 molar. So and that's your starting concentration. And so the solution is made by diluting 150 milliliters of 0.12 molar ferric nitrate solution with water to a final volume of 0.5 liters. Now, if you look at the problem, you'll notice you have 150 milliliters and 0.5 liters. You always want to have the units to be matching. And especially when you're first starting out, you should always have the units molarities and liter. So 150 milliliters, I'm going to put that down for your V1. That's your starting volume. But if you notice, this is a unit milliliters. We need to get this into unit liters. The units have to match. So you have to do a little conversion where 1 liter is equal to 1,000 milliliters. So technically this is all over 1. Milliliters will cancel out. So 150 times 1 divided by 1,000 is equal to 0.15 liters. So now we have the unit in liters. And we're trying to solve for calculate the molarity. So we don't know what this is, but this has been diluted to 0.5 liters. So again, if you notice, the volume should always go up, but one thing that should also happen here too is the concentration should always go down. So whatever answer we have here should be less than whatever we have here. So write out the equation. C1 V1 is equal to C2 V2. We don't know the concentration. We don't know C2. So this is what we're going to solve for. So C2 is being multiplied to V2. I need to make that stand by itself. So I need to divide both sides by V2. V2 over here will cancel out. So therefore, C2 is equal to C1 times V1 all over V2. And then just matter of plugging in the numbers. C1 is 0.12 molar. V1, you want to use the liters, 0.15 liters. V2, 0.5 liters. Now if you look at the units, the unit liters will cancel out. You're left with the unit molarity, which is a unit of concentration. So again, you multiply the top, you divide the bottom. So 0.12 times 0.15 divided by 0.5, you end up getting 0.036, and the unit left over is molarity. This is molarity. So this is 0.036 molar. Alright, so again, just kind of double check. The concentration should always get less. So you want 0.12 to 0.036. So that's what happened there. And the volume should always get larger, 0.15 to 0.5. So the volume ended up getting larger here in the process. Now the one thing to relate this to what we've already done before, this is not part of the question here. So this is your answer here. If you remember, molarity is equal to a mole per liter. If you rearrange this and solve for moles, that is equal to a mole is equal to the molarity times the liters. In other words, if you take 0.12 times 0.15, you're going to end up with an answer here. I don't have my calculator with me, but it will tell you how many moles you have here. If you take 0.036 times 0.5, these two moles should be the same. So in other words, if you take 0.12 times 0.15, that will be the same thing as 0.036 times 0.5. So in other words, the moles on this side will equal the moles on this side. All right. So in other words, the total number of particles did not change, and that goes back to when we're looking at this analogy here. Is that each one of these dots represents a mole. So even though I diluted it, the total number of particles still remained the same. So even though I was able to start off with a small volume, but I had a high concentration, by adding more water to it, I increased the volume, but I decreased the concentration. But the total number of moles will remain the same. In other words, I have 4 moles here, will equal 4 moles on this side over here. And the same thing is true with this. As you take these two, multiply them together, it will give you the moles. Take these two, multiply together, it will give you the moles. The moles here will equal the moles here. All right. So let's go ahead and move on to the next question. Number 2. You need 250 milliliters of a 0.2 molar sodium chloride, but the only supply of sodium chloride you have is a solution of 1 molar sodium chloride. Calculate the volume you must dilute the stock solution. All right, you need 250 milliliters of a 0.2 molar sodium chloride, and what you have is a 1 molar sodium chloride solution. So the fact that you need it, that's what you want at the end. So that's your after. But you have 1 molar. That's before you make any changes. So again, we're going to put down, this is your before, this is your after, and so you have C1, V1, and this is C2, V2. So you need 250 milliliters. So that's your volume. And you also need 0.2 molar. So that's what you need at the end. You have 1 molar. So the question is, how much do you have to take out of it to give you that concentration? So, and again, if you look at the answer here, or the units of this, you have milliliters. We need this in the unit of liters. So 1 liter is equal to 1,000 milliliters. This is all over 1. This way milliliters will cancel out. 250 times 1 divided by 1,000 is 0.25 liters. All right, so again, C1 V1 is equal to C2 V2. We don't know V1. So in order to make V1 stand by itself, we have to divide out the C1. So divide both sides by C1. These two over here will cancel out. So therefore, V1 is equal to C2 times V2, oops, there should be a 1 right there, all over C1. Now if you plug in the numbers, C2 is 0.2 molar, V2 is 0.25 liters, C1 is 1 molar. So if you look at the units, molarities will cancel out. So you're going to take 0.2 times 0.25 all over 1, end up getting 0.05 liters. So the unit left over here is liters, therefore the answer here is liters as well. So you have 0.05 liters. So basically what that means is that if you have a solution, now before I explain that here, a lot of times whenever you're taking a measurement, very seldom, if you remember, when you're looking at a beaker, most often the units are not in liters, they're in a unit of milliliters. So to find out how many milliliters, that would be 1,000 milliliters is equal to 1 liter. Now even though the question doesn't ask it, but some of the questions will ask this type of question, is that liters will cancel out. So 0.05 times 1,000, that is 50 milliliters. So what that means is that if you have a stock solution that is 1 molar, okay, this is a 1 molar solution. In order to make this solution over here, I need to first take out of here the 1 molar solution, and the amount I need to take out is 50 milliliters. Now when I first pour out that 50 milliliters, that solution is 1 molar. I don't know if you can see that here, but I have 1 molar right here. But then if I bring the volume up to 0.25 liters, or 250 milliliters, I would have diluted the solution here. It would have gone from 1 molar to now being 0.2 molar. So that's what this represents here. And this is something I have to do quite a bit in labs here, is I will have a A stock solution will have a certain concentration, and then I need to make it something more diluted, and I need to have a certain amount of it. So I had to figure out how much do I have to take out of the original container to give me that concentration. So this is something I have to do quite a bit here. For example, like hydrochloric acid, it's 12 molar when I purchase it. But what you end up using in class is anywhere from 1 to 0.25 molar. So I had to, and by multiplying by however many students I have here, that'll give me the volume. So there's a certain concentration, I need to have a certain volume, I need to know how much do I have to take out of it to give me that concentration and that volume. Okay, so let's move on to the next one. Number 3, you have a 2 molar sodium chloride. Calculate the volume you must dilute the stock solution to make 500 milliliters of a 0.5 molar sodium chloride. So you have a 2 molar sodium chloride. So let's start off with what's given to you here. So you have your before and after. I'm not going to write down the before and after, but just C1, B1, and then your C2, B2. I would recommend always writing this part down. This way you know what you have on hand. So you have 2 molar. In other words, that's what you're starting off with at the very beginning. So it's 2 molar. Calculate the volume you must dilute the stock solution to make 500 milliliters of a 0.5 molar sodium chloride. So you want to make it into a 0.5 molar. Now if you double check, 2 to 0.5, the concentration is going down. That's a good thing. And also you want to make 500 milliliters. So that's what you want at the end. Now, again, if you look, you have the unit milliliters. We need to get that into unit of liters. So 1 liter all over 1,000 milliliters. This way, milliliters will cancel, which will give you 0.5 liters. And we don't know how much we have to take out of here. So again, C1 V1 is equal to C2 V2. We don't know V1. So we had to make V1 stand by itself. And we'll divide both sides by C1. These two will cancel out. So therefore, V1 is equal to C2 times V2 all over C1. And then it's just a matter of plugging in the numbers here. So C2 is 0.5 molar. V2 is 0.5 liters. C1 is 2 molar. Molarities will cancel out. So 0.5 times 0.5 divided by 2 ends up come out to be 0.125 liters. Now even though it's not asking for it, let's go ahead and convert that into milliliters. So 1,000 milliliters all over 1 liter. Liters will cancel out. So that's the same thing as 125 milliliters. So the answer is 0.125 liters, which is the same thing as 125 milliliters. So this is your answer here. So again, if you notice, your concentration went down, but your volume went up. So in order to make 0.5 molar and have a 0.5 liters, if I have a 2 molar solution, I need to first take out 125 milliliters. And then once I pour out 125 milliliters of it, I want to bring the volume up to 0.5 liters to give me a 0.5 molar concentration. Number 4, you need to make 2 liters of a 0.2 molar magnesium sulfate from a 0.5 molar magnesium sulfate. How much must you dilute the stock solution? You need to make 2 liters of a 0.2 molar magnesium sulfate from 0.5 molar magnesium sulfate. How much must you dilute the stock solution? So again, C1, V1 is equal to C2, V2. And it doesn't matter what the solution is. So whether it's sodium chloride, hydrochloric, magnesium sulfate, whenever you're doing a dilution, it's always a proportionality. So you're just always using this part right here. So the actual substance really doesn't matter. So you need to make 2 liters. In other words, and if you need to make it, that's what you want to end up with. So I need 2 liters, and I also need 0.2 molar. And the original stock solution is 0.5 molar. And again, the question is, how much of the stock solution do you need? So that's what we need to try to solve for V1. So it's basically the same thing what we did previously. So you have C1 V1 is equal to C2 V2. Again, we're trying to solve for V1. So we need to get rid of C1. These two will cancel out. So V1 is equal to C2 times V2 all over C1. So if you plug in the numbers, C2 is 0.2 molar. Oops. 0.2 molar times V2, which is 2 liters, all over C1, which is 0.5 molar. So 0.2 times 2 divided by 0.5. And if you look at the units, milliliters will cancel out. So you end up with the unit of liters. And so when you do that, you end up with 0.8 liters. Now, let me put this down here. So 0.8 liters, convert that into milliliters. So 1,000 milliliters all over 1 liter. This is all over 1. So liters will cancel out. 0.8 times 1,000 divided by 1 is 800 milliliters. So you need 0.8 liters, or same thing as 800 milliliters. So again, what that means is that you have a stock solution that's 0.5 molar in concentration. You need to take out 800 milliliters, and then we'll still have a concentration of 0.5 molar. And then you need to bring the volume up to 2 liters. When you do that, this will no longer be 0.5, this will now be a 0.2 molar concentration. All right, let's move on to the next one. Number 5. You have 4 molars of potassium nitrate. Calculate the volume you must dilute the stock solution to make 50 milliliters of 0.2 molar potassium nitrate. So you have 4 molar of potassium nitrate. So that's your C1. So C1, V1, C2, and V2. So you have 4 molars of potassium nitrate. Again, the substance itself does not matter. Calculate the volume you must dilute the stock solution to make 50 milliliters of a 0.2 molar potassium nitrate. So it's very similar to what we've already done before. So we need to make a 0.2 molar, and we need 50 milliliters. And we don't know what V1 is. This won't always be an unknown. And any one of these 4 can be an unknown. Just so happens a lot of these, for several of these, have been where we had to solve for V1. All right, so we have C1 times V1 is equal to C2 times V2. And we're trying to solve for V1, so we need to divide both sides by C1. Now V1 is by itself. So C2 times V2 all over C1. So C2 is 0.2 molar. Now, we have 50 milliliters. I need to get this in the unit of liters. So 1 liter is equal to 1,000 milliliters. This is all over 1. Milliliters will cancel out. So that is equal to 0.05 liters. So that's why I want to use over here 0.05 liters. All over C1, which is 4 molar. So if you check the units, the molarity will cancel out. And when you 0.2 times 0.05 divide by 4, you end up getting 0.0025 liters. Now, that's kind of an unusual number here, so let's convert that into milliliters. So 1,000 milliliters all over 1 liter. Liters will cancel out. This is technically all over 1. So that comes out to be 2.5 milliliters. So you will end up with 0.0025 liters, which is the same thing as 2.5 milliliters as your final answer. And again, what that means is that if you have a 4 molar solution, you need to pour out 2.5 milliliters and then bring the volume up to 50 milliliters. And in doing so, you will now have a 0.2 molar concentration. All right, let's move on to the next one. Number 6. It is necessary to make a 0.5 molar solution of hydrochloric acid from 250 milliliters of a 2 molar solution of hydrochloric. What is the volume of the new solution? So it's necessary to make a 0.5 molar solution of hydrochloric acid from 250 milliliters of a 2 molar solution of hydrochloric. What is the volume of the new solution? So start off with C1 and B1 and C2 and B2. Okay, so we have a 2 molar. Start off with a 2 molar and 250 milliliters. And it's necessary to make 0.5 molar. In other words, that's what you want to end up with. So the question is, how much would you have? So if you took 2 molar and 250 milliliters of it, how much must you dilute it to give you a 0.5 molar? So C1, B1 is equal to C2 times V2. V2 is unknown, so you have to make it stand by itself. So you have to divide both sides by C2. So these two will cancel out. So therefore, V2 is equal to C1 times V1 all over C2. So you just plug in the numbers. C1 is 2 molar. V1, now this is in milliliters. I need to get this into liters. So 1 liter all over 1,000 milliliters. It's all over 1. These two will cancel out. Gives me 0.25 liters. So I need 0.25 liters all over C2, which is 0.5 molar. So if you check the units, molarity will cancel out. It's going to leave you with a unit of liters. So 2 times 0.25 divided by 0.5 gives you 1. That'll be 1 liter. And if you need to convert that into milliliters, 1,000 milliliters all over 1 liter. Liters will cancel out, which is the same thing as 1,000 milliliters. So this would be 1 liter or 1,000 milliliters. So if you took a 2 molar solution and you measure out 250 milliliters and you brought the volume to 1,000 milliliters, you'll have a 0.5 molar concentration. Number 7. What is the final volume of a solution if 500 milliliters of a 3 molar solution of sulfuric acid is to be diluted to a concentration of 0.5 molar? So in this situation, you're trying to make what's the final volume of a solution if 500 milliliters of a 3 molar solution of sulfuric acid is to be diluted to a concentration of 0.5 molar. All right, so we have a, let's start with what's given to you. C1, V1, C2, V2. All right, so you have a 3 molar solution, and you have 500 milliliters of it. And you're trying to make a 0.5 molar concentration. So the question is, what volume must you dilute it to give you that concentration? So if you notice your milliliters, we need to get that into unit of liters. So 1 liter all over 1,000 milliliters is all over 1. Milliliters will cancel out, so that's 0.5 liters. And then set the equation, C1 V1 is equal to C2 V2. V2 is unknown, so we need to get rid of the C2. These two will cancel out. So therefore, V2 is equal to C1 times V1 all over C2. So plug in the numbers. We have 3 molar. We have 0.5 liters. And the C2 is 0.5 molar. This way molarities will cancel out. So 3 times 0.5 divided by 0.5. And if you look at it, you should very quickly see that would be 3 liters. These two will cancel out here anyway, just leave you with 3. And the unit left over is liters. Or, to convert that into milliliters, 1,000 milliliters is all over 1 liter. Liters will cancel out because this is over 1, which will give you 3,000 milliliters. So you'll need 3 liters or 3,000 milliliters. Now, there are some situations where you actually have to solve for C1, and if you end up taking Chem 2, when we get into a thing called spectroscopy, there are ways where you actually find out this concentration, and if you knew how much you dilute it by, you can find out what is the original concentration. We have some labs here where we actually have to work backwards to find out what is this concentration. And it's worked out exactly the same thing that we've been doing here before. So let's move on to the next one. Number 8. What is the molarity of a solution which has a volume of 1,500 milliliters if it was obtained by diluting 250 milliliters of a 6 molar solution of sulfuric acid? All right, what is the molarity of a solution which has a volume of 1,500 milliliters if it was obtained by diluting 250 milliliters of a 6 molar solution of sulfuric acid? So C1 V1 is equal to C2 V2. All right, so we have a 6 molar. We start off with 6 molar, and you have 250 milliliters. And you're trying to dilute it down to 1,500 milliliters. Now, if you notice, your units, and you get to use into unit of liters. Now, you could actually do it without here, but I still just want you to get in the practice of doing this. So milliliters into liters, so 1 liter over 1,000 milliliters. It's all over 1. Milliliters will cancel out. So that's 0.25 liters. Same thing with this. 1 liter all over 1,000 milliliters. Milliliters will cancel out, so that gives you 1.5 liters. And the C2 is unknown. So C1 V1 is equal to C2 V2. Trying to solve for C2, so we had to get rid of the V2. These two will cancel out. So therefore, C2 is equal to C1 times V1 all over V2. So C1 is 6 molar. V1 is 0.25 liters. V2 is 1.5 liters. You notice liters will cancel out. So 6 times 0.25 divided by 1.5 comes out to be a 1 molar concentration. Alright, so concentration of this would be 1 molar. Again, if you notice, concentration should go down. It should go down, and the volume should go up. Number 9. To prepare 250 milliliters of a 0.1 molar solution, how many milliliters of a 4 molar calcium nitrate solution must be used? So let's start off with C1, V1, and C2, V2. Now, you're trying to prepare 250 milliliters of a 0.1 molar solution. So the question, since you're trying to prepare that, that's what you're trying to end up with. So you're trying to end up with a 0.1 molar and 250 milliliters. And you're want to know how many milliliters of a 4 molar calcium nitrate. So we don't know this value here. And you're starting with a 4 molar concentration. So we have C1 V1 is equal to C2 V2. We don't know V1. So we need to get rid of the C1. So therefore, V1 is equal to C2 times V2 all over C1. So C2, now, as before we do that, let's go ahead and convert this into liters. So 250 milliliters, so 1 liter over 1,000 milliliters. Milliliters will cancel. So you end up with 0.25 liters. So your C2 is 0.1 molar. Your V2 is 0.25 liters. Your C1 is 4 molar. Now, the molarity will cancel out. So 0.1 times 0.25 divided by 4 comes out to be 0.00625 liters. Now, if you look at the question, it wants the answer in milliliters. So we need to convert this into milliliters. So 1,000 milliliters is equal to 1 liter. This is all over 1. This way liters can cancel out. So 0.00625 times 1,000 comes out to be 6.25 milliliters. So that's your answer. So this time it specifies, not liters, milliliters. So this time it specified how many milliliters is it. If it doesn't tell you, a lot of times just leave it in the unit of liters. So in other words, if you have 4 molar, and if you measure out 6.25 milliliters, and you brought the volume up to 250 milliliters, you will have a concentration of a 0.1 molar solution. So let's move on to the last one. Number 10. When 400 milliliters of a 2 molar solution of sodium hydroxide is diluted to make a 0.1 molar solution, what will be the final volume? As you notice, all of these are basically the same thing. So C1, V1 is equal to C2 times V2. Alright, so for this last one, you have 400 milliliters of a 2 molar solution of sodium hydroxide, and you're trying to make a 0.1 molar solution. So since you're trying to make that amount, that's going to be your 0.1 molar. Okay, but when you have 400 milliliters, that's your volume, of a 2 molar solution. That's this part right here. And we're trying to find out how much must you dilute it to give you that concentration. So let's go ahead and convert the milliliters into liters. So technically this is all over 1. So therefore 1 liter all over 1,000 milliliters. Milliliters will cancel out, and that will give you a 0.4 liter solution. Alright, so now C1 times V1 is equal to C2 times V2. We're trying to solve for V2, so we had to get rid of the C2. So C2s will cancel out. So V2 is equal to C1 times V1 all over C2. So C1 is 2 molar. V1 is 0.4 liters. And C2 is 0.1 molar. Alright, and if you check the units, milliliters will cancel out. We'll leave you with the unit of liters, which is a unit of volume. So 2 times 0.4 divided by 0.1 will come out to be 8 liters. Or we convert that into milliliters. 1,000 milliliters is equal to 1 liter. This is technically all over 1. So therefore you would have 8,000 milliliters. So therefore it will take you 8 liters, or the same thing as 8,000 milliliters, for you to create this 0.1 molar solution. So if you have 2 molar and you have 0.4 liters of it, or 400 milliliters of it, you must dilute it to 8,000 milliliters, or 8 liters, to give you a 0.1 molar concentration. So hopefully that made sense. On your Moodle homework, basically whenever you're seeing a dilution here, the main thing is that whenever you're dealing with a dilution, look for where the volume is going up and the concentration is going down. So if you see something set up where you either have like 2 concentrations or 2 volumes, chances are you're dealing with a dilution problem. So you're going to be doing this type of calculation. And pay attention also, if it's asking for milliliters, make sure that you do something like this step right here. Now if it doesn't say for you to do so, then just leave it as liters. Alright, that concludes this section of the chapter. Make sure that you complete the Moodle assignment and the questions on there, and then we'll be moving on from there. If you have any questions, please let me know. You guys take care. Bye-bye.